Okay, good afternoon. Let us start our lecture. So yesterday we talked about distribution of a random variable. So a distribution of a random variable tells you everything about the random variable. All right, so you can compute the probabilities of x falls within certain range. All right, but there are two types of random variables from the computation or understanding of the distribution. They are discrete and continuous. So basically, for discrete random variable means that the values of the x of the random variable x are discrete. That means they got gaps in between. Okay, usually they are integers. While for continuous random variable, the x values take over part of the real line or the whole real line, or take over an interval. Okay, you have to distinguish between the two because the computational methods are different for different types of random variables. So for discrete, you have to do the addition, while for continuous, you have to do integration. All right. So, we also talk about something called distribution. All right. So we have probability function f of x, which basically equal to probability of x equal to x for discrete random variable. While for continuous random variable, we have the probability density function. I asked you a question about probability density function now. What was the question now? Huh? You forget. I forget. So what's the question? Anyone remember? For the probability function, because it is equal to the probability of the random variable takes certain values, so it has to be between 0 and 1. So my question for probability density function, which is for continuous random variable, my question is, can this bigger than 1? That means, can the density be bigger than 1? All right? So you forgot the question, so you did not try. Okay, the answer is yes. Why? I can give you a very intuitive example. Now, for normal distribution, it's from minus infinity to infinity. If you still remember what normal distribution is, with this bell shape. So the area under this bell curve, because this represents the density, and integrate over from minus infinity up to this point represent the probability less than it. So this will be the probability less than this value. So this value can be infinity, but the probability is still between 0 and 1. So in other words, the area under this bell curve or the normal PDF is 1, right? So now, for another situations, just between 0 and 0.5. The rest of the PDF takes value 0. So, and it's flat. So, in other words, I want this area to be 1. The width here is 0.5. So what is this height? 2. 2 times 0.5 gives you 1. So in other words, the density, remember it's the density, it's not the probability, it's the probability density. It represents how dense the probability is. So it can be bigger than 1. Because you have a smaller range or smaller width. So when you multiply it, the total area is still 1. All right? So I want you to distinguish both are fx, lead to fx. For discrete random variable, it represents the probability at that particular point. While for continuous, it only represents the density at that point. And then in order to convert it to probability, you have to consider a very small neighborhood of this point, x between x and x plus delta x. Then this width times the density will give you the probability that the random variable lies between x and x plus delta x. All right, so that's the density function. All right, so this probability function or probability density function will identify the distribution. But there's one what we call cumulative distribution function. Distribution function. Sometimes we just write it as CDF. Use capital letter to represent it. It is equal to a probability of the random variable less or equal to x. Which means that this basically is the probability of the random variable less or equal to x. So the definition is there. Fit can be applied to both discrete and continuous random variable. All right? And this one is true for all x. Whether it's discrete or continuous is defined as this one. So that is the CDF. All right? So today we see some examples of this CDF. Okay, here's the first example. So we are given the probability function of the random variable x given by the form 1 minus p raised to power x minus 1 times p. All right? Where x equal to 1, 2, 3, 4 up to infinity. All right? If you're not familiar with the probability function given here, you should ask yourself, is this a well-defined probability function? Which means that you have to check two things. Whether the f of x is bigger than 0 for all x value. Bigger or equal to 0 for all x value. And what's the second condition we have to check? So all the probability function over all the x should equal to 1. All right? Because x can be 1, can be 2, can be 3, can be 1,000, can be 1 million. All right? But it has, all this probability has to add up to 1. All right? So, in fact, we have a name for this distribution. Anyone know what it is called? Have you seen something like this? It's something to do called geometric series. All right? The terms are multiplied by r from the previous one. So this is called geometric distribution. In fact, it represents the following experiment. You think of it, you have an experiment. So there are only two outcomes, failure or success, with a probability of success being p. So this basically represents a probability of some event. What is that event? I can describe it as the number of times that you perform the experiment. Okay, you can think of it, toss a coin. I want a hat. So I want a hat. Hat is considered success. Let's say P is the probability of getting a hat when I toss a coin. So I toss a coin. The first one is a hat. Then I stop. I got my hat. So basically this represents the probability of getting a hat the first time. So that means if the first one is a failure, then you try a second time and third time until you get the first success. All right? So x is the number of times that you try in order to get the first success. If x equal to 1, it means that the first time you toss it, you got a hat, a success. Okay? Then you may toss 3 times. All 3 failures, you continue to toss until you got it. So that's why it's 1 minus p raised to power x minus 1. That is the x minus 1 failures. Then times the last one is the success. So this is what we call geometric distribution. But we put that aside. We just try to look at it and try to do some thing about the CDF. All right? So there are infinite number of them. So we want to find the CDF. The CDF. So for any positive integers, I just sum up all the density, all the probability of t, f of t, such that t is less or equal to x. So remember the graph that I showed you. So if this is the discrete probability, so the CDF, all right, will be, for example, at this point, the CDF will be the probability that you collect when you come from minus infinity up to this point. So that, adding these two, will be the height of my CDF. So at integer x, then you have certain values. So basically it's something like this. All right? No such point, and so on. All right? So basically it's this is the f of t. All right? 1 minus p raised to power t minus 1 times p. Okay, then the next few lines are basically just mathematics. So how to do the sum? All right? The sum is summing up t from 1 to x. So in other words, you are summing up p times 1 minus p, 1 minus 1, plus p times 1 minus p, 2 minus 1, and so on until p 1 minus p, x minus 1. All right, so this is the sum. I basically write this whole thing in one expression using the summation sign. It represents sum of x terms. Okay, so p is a common factor. Every term has this p, so I take it out of the summation sign, bring it out. So it's 1 plus 1 minus p plus 1 minus p squared plus 1 minus p raised to power x minus 1. All right, so this is what we have. So in terms of summation sign, I bring the p out. All right. Then what I did is I change. This is from t equal to 1 to x. So now let me have s equal to t minus 1. I change. All right. So all the t will change to s. T minus 1 will change to s. So this becomes s. This one, t equal 1 means s equals 0. T equal to x means s equal to x minus 1. So it becomes like that. All right. Then I don't know whether you have seen this before. Do you know what is the sum of all this? This is equal to 1 minus r n plus 1 over 1 minus r. All right? So this is a geometric series formula. And if n goes to infinity, all right, then this will go to 0. So if this goes to infinity, then the answer is 1 over 1 minus r for n goes to infinity. That means n getting bigger. You add more terms, but the final answer is 1 over 1 minus r. Okay, but here I just for particular x, so this is the answer for particular x. But for CDF, cumulative distributive function, you also have to stay for any x value. So if you recall, let me go back to this graph. Yeah, this graph. So what I just showed you with the given probability function, I just evaluate all these points. Now the question is, what is in between? So obviously, the values which is not integer should have a CDF the same as the integer less or equal to it. All right. So in other words, if I want to know the CDF of this value, I go up and look for the CDF for the largest integer, which is less than what I have. Because from that point onward, I do not have any probability to add in until I reach that point. And then I keep going until I reach the next integer, then I will go up, have additional probability. So So I do it step by step. First of all, I work out for integers. All right. Then for any values which is not integer, then I have to change this to a notation, square bracket x. This may not be universal. I just define it. A square bracket x means that it's the largest integer less than your x. Largest integer less than your x. Less or equal to your x. All right. So if, for example, 2.7 means 2. If 3, it means 3. All right. So this is the CDF. All right. Why? Because this one, you see, 1 minus 1 minus p, so it becomes p. So p cancel with this p. So the CDF is equal to this. For x is an integer. So this one we know. Then the next step, how about in between the integers? What is the CDF? So we know the CDF properties. So it's for any x value which is not an integer, then it's equal to the f of x. For that x is the largest integer less or equal to your x. So that is how you get the CDF. Okay, here's another example. Okay, so we have this x represent the number of days of a sick leave for a particular or for a randomly select employee who take. So this employee may take 0-day leave or 1 day or up to 14 days. All right, up to 14 days. You can take more than that, but only 14 days counts. Okay, the company only counts 14 days. Okay, and then suppose from the past experience, we know that f of 0 is 0.58, f of 1 is 0.72. Now this capital F represents a CDF. So in other words, this is the probability of x less or equal to 0. This one is the probability of x less or equal to 1. So this number must be bigger than this number, and so on. So what we are given up to F5. F5. Okay. So what is F6? We don't know exact value. But at least we know something about it. What can I say about f of x, 6? It must be greater or equal to 0.94, right? Okay, so we don't know what capital F6 is, but we know that it must be greater or equal to 0.94. How about F14? Do we know? 1. Right? Don't say that. I don't know. Or I just, okay, my question is, what is F14? All right? F14 is equal to 1. We know. It's not just bigger than 0.94. We know it's 1. Why is it 1? Because that's all the possible values for x. So it has to be 1. All right? So based on this one, we try to answer the questions. All right? What's the chance that x falls between 2 and 5? So a particular employee whose day of leave is between 2 and 5 inclusive. So it's equal to F5 minus F2 minus, okay? So in other words, it is probability of x less or equal to 5 minus probability of x less than 2. Does not include 2. You have to subtract this part. So this is represented by F2 minus. Because we are working on the random variable x, which are integers, it takes integer values. So therefore, 2 minus basically means 1. This is equal to F1, equal to the value of x value, which is the largest integer less than 2 minus, which is 1. All right? So the answer is 0.22. Then how about x equal to 3? We are not given little f3, but this is equal to f of 3, probability x less or equal to 3, minus probability of x less than 3. These two are not the same. If they're the same, then simply means that x cannot be equal to 3. the probability is 0 because the difference represents the probability of x equal to 3. So it's equal to this minus this, which is 0.05. All right? Okay, another example. So we have to check this incoming materials for defects. And we look at a lot of 5. Then we select 2 out of these 5 items, check for defective. So we're asked to list all possible inspections. So basically you have a lot which have 5 items, and I select 2. So how many ways that I can select, and not how many ways, you have to list out what are these ways, what are these possible items being selected. And then also suppose, suppose the box 1 and 2 are the only defective in a lot of 5. I'm sorry, it's a little bit confusing. I should replace it by A and B, maybe better. So the 5 items are represented by A, B, C, D, E. So first of all, we are asked, select 2 out of these 5. How many ways? Not how many ways, but list all possible ways of inspection. So one way is like A, B. The order is not important. Or A, C. Or the last one is D, E. So these are the possible ways of select 2 out of these 5. Okay, in my notes, I use 1, 2, 3, 4, 5. All right. So, okay, so now if X represents the number of defective items among the 2 that you select, all right, then we have to work out what is the probability function or the CTF of this random variable X, and then based on that we can answer the question about X equal to certain values or certain events. So we're asked to find the probability distribution of X. All right. Then we obtain the CTF for all X. Remember, for all X. All right. So the first one is straightforward. We select 2 out of 5. So answer is 10. And these are the possible. All right. So so it basically is A, B, A, C, and so on. So 10 of them. And the order is not important, although I use the order pair, but the order is not important. So altogether 10 possible choices. Okay, so X is the number of defectives in the sample of 2 items. So the number of defectives can be 0, can be 1, can be 2. Shouldn't go beyond that. All right, so now the question is, what is F0? So F0 means probability of X equals 0. No defectives. No defectives means that you don't have 1 or 2. Item 1 and item 2 in your sample. So only this one. All right? So altogether there are 10 possible ways, and 3 of them will give you no defectives, so it's 3 out of 10. Next, we work on F2. All right? All the 2 items are defectives, so that means you have only one choice, 1, 2. All right, you choose 1 and 2 together, so it's 1 over 10. And then I work out the F1. Because there are only 3 possible values for X, so F1 is just 1 minus F0 and F2, so it's 6 over 10. You see, by doing so, you see, I did not follow F0, then F1, then F2. I work F0 and then F2, then F1 is obtained by 1 minus F0 and F1. So it's much easier. Because if you work this directly, you have to know, which of them means 1 defective. So this means 1 defective, 1 defective, 1 defective, 1 defective, 1 defective. So you have to count. Sometimes you may miss out. So try to take an easier way. So in this case, you work out F0, F2, and then subtract those from 1. All right? Getting a habit that although we know that X can only be 0, 1, 2, but in order to specify your probability distribute function, you also name for all other X value. All right. So long as x does not equal to 0, 1, and 2, then f of x equal to 0. All right. It looks not so important, but you get a habit that you define for all the x values. All right. Then the CDF. So the CDF, you're supposed to work on all x values. But for discrete case, you basically just work on those x values that you have non-zero probabilities. So in this case, you just need to work out F0, F1, and F2. All right, just these three values. So automatically, the in-between will show up. All right, so in this case, for capital F0 is equal to 0.3. F1, you have to add up x equals 0 and x equal to 1, so it's 0.9. And F2, x less or equal to 2, so it's 1. All right? So we have these three values. Because it's discrete, so any x values between 0 and 1, for example, f.6, it should equal to f0, which means that it is 0.3. All right? So f.99 also equal to f0, so it's equal to 0.3. All right? So we summarize these results into a function like that. So that altogether, 4, I divide the real line into 4 parts. So from minus infinity up to 0, but less than 0, I haven't reached 0, the probability, the cumulative probability is 0, because we don't have probability for those x value less than 0. But once we reach 0, we jump 0.3. All right, so the CDF now is at this point. Then for x between 0 and 1, but less than 1, then you do not collect any more probability, so therefore it is flat. All right, so this means that any value between 0 and 1, the f of x is 0.3, and so on. So it's a step function. It's a step function. 1, 2, 3. All right? So for x greater than 2, greater or equal to 2, the CDF is equal to 1. All right? So in other words, for any x value, you can work out what is the CDF. So f minus 1 is equal to 0. f5 is equal to 1. All right? Because I substitute 5, so means that f of 5 is equal to 1. So that is for discrete random variables. So unlike in example 1, in example 1, I have a formula for it. So here, I don't have the formula. I have to specify what is this CDF x over a certain range. So altogether, I divide the real line into 4 parts, 4 regions. All right. Example 4. So the PDF is, okay, now the distribution is a continuous distribution because we are talking about x between 0 and 1. And the density function is given by a formula, which is 2x. And beyond that, it is 0. All right? So basically, it represents something like this. So the PDF, f of x, all right, is 0 here, but then it is a slope here. So this represents y equal to 2x. All right? Okay, so find the CDF. So naturally, what we do is for any x, we just integrate f of x is equal to integrate from probability of x less or equal to x, which is to integrate from minus infinity up to x, ft dt. All right, so this is a standard formula. So you must start with this one. The question is, what is ft? And ft have 2 forms. When x or when t is between 0 and 1, it takes the form 2t. When t is outside this range, it's 0. So you have to take this into consideration when you do the integration. So when x is less than 0, f of t equal to 0. When x is between 0 and 1, then f of t equal to 2t. All right. I have to separate this integrate from minus infinity to x into two parts for this range. One is from minus infinity to 0. All right? Remember, this is the graph, right? So if x is here, I have to integrate this part with f of t equals 0. Then integrate this part with f of t equal to 2t. And when x bigger than 1, then I have to separate the region into 3 parts. So now, if x is here, then I have to divide it into from minus infinity to 0, then from 0 to 1, because from 0 to 1, the f of t equals 2t. Beyond 1, then the density is 0 again. So I have to do the integration. Don't be lazy. Don't use one form of the function ft for the integration. You must separate into different regions. Consider different ft for different region. Okay, after you complete the integration, this is the answer. So the CDF equal to 0 if x is less than 0 and equal to t squared, so x squared, all right, when x is between 0 and 1, and equal to 1 when x is bigger than 1. Okay, so here's another example, basically the same idea, but this time the PDF defined for positive x, all right? Wow, very complicated, huh? Okay, so this stress, vibratory stress given by this PDF. Oh, by the way, now I write it in this form simply to say that, okay, I'm still looking at f of x. But this f of x, this function has another quantity, which is theta. So this basically is a function of x and theta. But I will look it from the following, as follows. I will look at it as a probability density function, x. X is the value of the random variable. But the theta is part of the PDF, okay, which is a constant. We call it parameter, which is a constant. It does not, it's not vary randomly, so it's not a random variable. All right, so this is a fixed constant. If you don't like theta, you can call it A or call it C. It's just a constant. All right. Okay, so we have to verify that this is a legitimate PDF, which means that it has to satisfy two conditions. F of x, the first one is f of x has to be bigger or equal to 0 for all x. Second part is integrate from minus infinity to infinity, f of x dx has to be 1. So you have to check these two. In order to show that PDF here, the form that we have is really a PDF. Second, here, now we replace theta by a number, 100. All right? So suppose theta equal 100, then what is the probability of x at most 200? That means what is the chance that x at most 200? Less than, right? Less than 200. Less than 200. Right? Is it? And at least 200. At least 200. Must bigger than 200. So these are the probability that we are asked to find. Okay, since it's continuous, basically these two are the same. All right, we also try to give an expression for the CDF. This is a CDF, all right? Before we get all this, the last part, the CDF, it should be in terms of x as well as should have a theta there. Your function should have x and theta for part C. Okay. Then find the probability of x between 100 and 200. That is, we try to look for probability of x between 100 and 200. All right? Okay. So first condition is obvious. For f of x is bigger than 0. You can see that I mentioned it yesterday, e to power any function, e to power whatever, a or minus a, all right, is bigger than 0. How about this part? This is bigger than 0, theta square. X is, how about x? Does x take the value bigger than 0? Yes, because the way that we define the PDF, x has to be bigger than 0. So therefore, the whole thing is positive. So obviously, the first condition met. The second one is to have to do the integration. So we integrate from minus infinity to infinity the PDF over x, all right? But this one, in fact, can be written as from minus infinity to 0, 0 dx, plus from 0 to infinity, the f of x, which is x2 theta, sorry, theta square, e to power minus x square over 2 theta square dx. All right, the PDF are different over different range. For negative x value, this means x between minus infinity to 0, the PDF is 0. For x being bigger between 0 and infinity, this is the probability density function. So that's why integrate this one is equal to integrate this one. You must know why. All right. The first, okay, the one on the left, all right, can be broken down into two parts. Integrate from minus infinity to 0, and the other one is from 0 to infinity. Why we have to do that? Because the PDF has a different form over these two regions. Then, so it's equal to integrate from 0 to infinity, differentiate e to the power minus x squared over 2 theta squared. This one is quite obvious, because if you differentiate this one with respect to x, you will get this part. All right. So once you have this, then obvious. What it means is that you differentiate this part and then integrate. So it just means that you are getting back this function. All right. This is the function. You differentiate with respect to x, but then later you also integrate. So that means you take the inverse function. So the answer will be e to the power minus x squared over 2 theta squared. All right, the integration. And lower limit is 0, the upper limit is infinity. All right. What is this? Integrate dx. So this is equal to x. Because you differentiate this one and then you integrate, so you call back x. Plus constant, all right? But if it's it is a definite integral, then you have to just substitute the limit. If it is from a to b, forget about the c, then you just substitute a and b. It becomes b minus a. All right, so if you have problems doing this integration, you go and revise your calculus. All right, how to do the integration. These are very simple integration. So the answer turned out to be 1. All right. Substitute when x goes to infinity. So this one goes to infinity, but you have minus. So it's e to the power minus a, and a goes to infinity. So this one equal to 0. If a go to infinity. Substitute 0, you got 1. All right? So, so it's 0 minus 1, so it's 1. All right? Okay. So, so we're asked to find the probability of x less or equal to 200. So we integrate from minus infinity to 200, which can be written as integrate from minus infinity to 0 plus from 0 to 200. All right, x over 100 squared e to the power minus x squared over 2 100 squared dx. All right, so you just repeat what we just did. So differentiate this part will give you this. So, so this is what we have. Substitute 200 in it, you got e to the power minus 2. Substitute 0, you got plus 1. So the answer is 0.8647. So in other words, the chance of this x falls between minus infinity to 200 or less or equal to 200 is equal to 0.86. All right? Because it's continuous, so therefore this answer, all right, at most 200 and less than 200, they are different events. But for continuous random variable, they are the same. The probability are the same. I have to stress that. I did not say this event and this event are the same. It's only the probability of these two events are the same. Because the probability of x equal to 200 is equal to 0. All right? All right. Then x greater or equal to 200 is equal to 1 minus. Okay. I'm sorry, maybe strictly speaking, this should be less than 200. Less than 200. So that is a complement of each other. But because it's continuous random variable, so it may not, it won't affect your answer. But strictly speaking, it should be less than 200. All right? Then find the CDF. So we just do the integration. And now this, you have to be careful. Because we are working on f of x. All right? X is fixed. X is fixed. While the integration, what you do on the integration, the variable, you try to avoid using x because x has a meaning here. X referring to this x value, this x. So therefore, we change the integration variable to t or any letter you want. So you just do the integration. So it's the same expression, but now the upper limit is x, the lower limit is 0. So we substitute. This is the CDF. Now, why we want the CDF? So just now we compute probability of x less or equal to 200. How about if I ask the same question? How about x less or equal to 149? Then I have to do the integration again. Why bother to do so many integration? I do the integration once. That's how I get the CDF. So once I have the CDF, all right, like that. This is true for all x bigger than 0. Then I substitute 149 into this place, then I will get the probability. All right? So, if I want to know what is the probability of x, all right, greater than 95, where x follow the PDF, distribute with the PDF given there. So this is equal to F95? Right or not? No. It should be 1 minus F95. Because this is equal to 1 minus probability of x less or equal to 95. And this is F95. So it's 1 minus capital F95. All right? Now how about another question? What's the probability of x between 50 and 75? Oh, if you do the integration again, then you have to do a lot of work. But then this is just F75 minus F50. Because it's continuous, so I don't really bother about the equal, whether it's less or equal or just less. So I don't really bother about that. So you just work out, substitute 75 into here, 50 into here, and then do the subtraction. All right. So this is exactly what we did. All right. So the answer for x, chance of x between 100 and 200 is 0.4712. All right. So this is the method that I mentioned. This is the PDF, and you integrate from 100 to 200. So you have to do the integration and substitute. So try not to do it. So once I got the CDF, I have done the integration. So the rest, how to find the probability, I just make use of this CDF and try to work out the probabilities. What is the probability of x equal to 100 in this example? 0 lah. Continuous random variable. So don't be over smart. Oh, F100 minus F100 minus. They're the same thing. All right? Because this only the 100, F100 and F100 minus make a difference, provided that the probability of x equal to 100 is non-zero. All right? So it may be non-zero only when they talk about discrete random variable. But even for discrete random variable, probability of x equal to 100 may be the same. So my point is, I got this answer. It's not from using the formulas to calculate. I just know that x is continuous random variable. So x cannot equal to any particular value. The chance that it's equal to a particular value, I should modify. The chance that it equals to a particular value is 0. The chance is 0. Okay. So now we move on to talk about something called mean and variance. You can think of it like this. The little f of x, or the probability function or probability density function, or the CDF, all this tells you how the random variable behaves. But maybe it's too difficult. It tells us so much, so many things. How do I know? I want to have a simple way to describe or understand the distribution. So one way is, give me a number. This number will illustrate the center of the distribution, or is a very popular region that the random variable takes the value. So it's sort of a center. All right. So mean, or the expectation of the random variable, is a quantity that illustrates where the center of the distribution is. All right. So for discrete case, so we start with discrete case. So what we have is this. So we have a bunch of values. All right. And if each value has their own probability, so some may have a bigger probability while the other associated with a small probability. Okay. So what we do is to take a weighted average. Each value weighed by their probability. All right, and then sum them up. So that quantity will sort of represent the center. So let's say I have 0, 1, and then 10. Okay, only 3 values. While the probability of getting 0 and 1 are 0.01 for each of these. So 0.01, 0.01 for this one, then 0.98 is 10. So among these 3 values, if this is my distribution, then I would say it's likely that this 10 is the one that dominates. So the center should be close to this 10. So that's how we do it. So it's value 0 times the probability plus 1 times the probability plus 10 times the probability. All right. So this value is close to 10. It's 9 point something. All right. So what I'm trying to say is that this expectation of x, which sometimes denote by mu, all right, this is to measure the center of the distribution. So for discrete case, you have so many possible values for x, you just weight each x value by its probability. All right. Then the most common one you encounter is if each one has equal probability, then it will be 1 over n. So it's just as if you add up all the values and then divide by n, the number of observations. That is a special case. Remember, this is a special case. The expectation should be defined as the value times the corresponding probability. So it's x times f of x. So expectation of x for discrete case usually is written as x times the corresponding probability function, and then sum up over all the possible x values. So that is the expectation of x, which sort of measure the center is. And this is a constant. It's a constant. X is a random variable, but expectation of x is not a random variable. It is a constant. All right? So sometimes it's denoted by the Greek letter mu. And it's called expected value. It's important. Whenever you see the mean, MEAN, then some of you may always think that, I just add up all the value and then divide by the number of observations. That is a special case of mean. Mean in probability and statistics basically depends on, for discrete, it is x times the probability of x. So in fact, it is basically a weighted average. All right? Remember, I gave you an example about the number of modules that the NUS student take. So it ranges from 1 to 6 or 7 with a different probability, different proportion, different probability. So you see that if you just take the average of the number of modules, 1, 2, 3, 4, 5, 6, 7 maybe, that average, it does not make sense. But there are fewer people take one module. More people take 5 modules. So we have give more weight to these 5 modules, or x equal to 5. So therefore, the expectation will be somewhere around 5 or 4 point something. All right. A remark. The expected value is not necessarily a possible values of the random variable. This is important. So don't expect your expectation of x is one of the values of the random variable x. Okay? Okay, for continuous, instead of doing summation, we do integration. You see, just for discrete case, it's like this. So for continuous case, we replace this summation by integration. Do the integration from minus infinity up to infinity. All right? So that is the definition for the expected values for x, random variable x. So just remember, expectation is the average, but more precisely is the weighted average. Weighed by what? Weighed by the probability function or weighed by the probability density. So, of course, the expected value exists provided that the sum or the integral exists. If it's not, it does not exist, that means there are no expected value for that. So for discrete case, if your f of x is 1 over n, where n is the number of values, then it becomes just like the usual practice, sum over all the observation and divide by n. So if you go back to the, where's my number of modules? What's the slide number? The number of modules that taken. Page 30, 40. This one. All right. Now, this is the number of modules from 1 module to 7 modules for NUS students. Altogether, we assume that is 35,000. So you can think of it like this. On one hand, you have 35,000 values. Each student has 1 value, the number of modules that they take. All right? So the average can be just add up all these 35,000 values. Some of them are 1s, some of them are 2s, some of them are 7s. So add them up and divide by 35,000. So that is the usual way that we compute the average. But now I interpret it as the number of modules x, all right, as a random variable, which can take the value 1, 2, 3, 4, 5, 6, 7 with a certain probability. So the chance of getting x equal to 5 is 0.39. So now what I do is to apply my formula for expected x. So it becomes 1 times 0.01 plus 2 times 0.03 plus 3 times 0.13 and so on. And then I get the number. So that is my expected number of modules that a student take. But for a particular student, it's either one of these 7 values. All right? But what I'm saying is that I expect, if I select one, I expect the value is somewhere, the answer that I obtained by doing the summation of this x times f of x. All right? So summing up all the values and then divide by the number of observations, that works when you have finite population. Think of it. All right? If I toss a coin, I don't know whether it's fair or not. So I don't know probability of getting a hat is, what value is it? So I have to toss it infinite number of times. So how do you get in some infinite number of numbers and then divide by a number which is a very also infinite? You cannot do that. But if I change it to a probability density or probability function, then I say that, okay, the chance I get a hat probability is half. The chance getting no hat is half. All right? Hat is 1 and no hat is 0. Then I can say, well, what is the expected number of hats? It should be 0.5. All right? I can do it this way. So what I'm saying is that getting a hat, x will take 1 and tail 0. And the probability, okay, let's put this as p. This is 1 minus p. So the expectation of x is 1 times p plus 0 times 1 minus p. So the answer is p. So I expect the number of hats that I got will be p. All right? But if you think of it, well, toss the coin 100 times and then divide by 100. Adding 100, 0 and 1s, divide by 100. Yes, you can do that. But then how about if I toss it 1 million times? So you have to add up the 1 million times. The outcome is either 0 or 1. 100 of the value which is either 0 or 1. And then divide by 1 million. So a lot of work. So you have to change the interpretation. So I'm talking about, okay, the chance of getting a 1 is p. The chance of getting 0 is 1 minus p. What do you expect? The expectation is x times f of x and then sum them up. Here I have only 2 values. X takes the value 1 and 0. The corresponding probability is p and 1 minus p, and then I work out the PDF. Sorry, the expectation of x is p. All right, so okay, so where are we? All right, so okay, let's look at an example. So in a game, I'm sorry we use this game to just illustrate the idea. So you will gain 5 if you get all the heads or all the tails when toss the coin 3 times. So there are 8 possible outcomes when you toss the coin 3 times. All heads and all tails, all right? Then this man will get 5, right? And his pays out will be, he had to pay 3 if either 1 or 2 heads show up. All right. Now, there are different layers. Let's just revise what we have for toss 3 coins. So the possible outcomes, 8. All right. We have to consider something like this. This is one possible sample points. This is another one. This is a third one, and so on. Now, these 2 are, if you don't identify the coins, basically there are 2 heads, one tails. All right? But why I have to distinguish them, to differentiate them? Why? Why don't you just say 3 heads, 2 heads, 1 head, and no head? You forgot one important thing. The sample points or the outcomes, are they equally likely? So if you have 3 heads, 2 heads, 1 head, 0 head, they are not equally likely. But if I write it as HHH, HHT, all right, head, tail, head, all these are equally likely. So altogether, there are 8 equal likely outcomes for this experiment of tossing 3 coins. All right, so that from there, we can work out the probability. So here, we are asked, what is the expected gain? Okay, now here, we are tossing a coin 3 times, or tossing 3 coins. All right, the outcome depends on the outcome. 3 heads, 3 tails, this man win $5 or 5 units. Well, otherwise, that means 1 head or 2 heads, then he has to pay 3 units or $3. All right. So what is his expected gain? His gain is a random variable. Will he get 5 all the time? No, only when got 3 heads and 3 tails, then he got $5. All right. So what he get, there are 2 possible values. One is 5. How about the other one? 3. No. Hey, if it's 5 and 3, then he's always make money. All right. He pays out. So he has to pay $3. All right. In order, if the outcome is 1 head or 2 heads. So X, okay, if we define X is his gain, all right, X is gain. It's a random variable. It takes the value 5 and minus 3. At the same time, you have to define what is the probability, what is F5 and what is F minus 3. All right. We can work it out. Because F of 5 simply means that it is the probability of getting tail, 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 or head, 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 which is 1/4, right? So how about getting paid $3 is 1 minus 1/4. That's one way to do it. Because there are only 2 possible outcomes. Either you gain $5 or you lose $3. All right? So it's just 1 minus 1/4. Or if not, then you just work out how many possible sample points give you 2 heads and how many possible sample points give you 1 head. Altogether, there's 6 out of 8. All right, so here is the answer. So therefore, the expectation equal to X times F of X. And then you sum them up. So it's minus 1. So he may not expect, but we know that on average he will lose $1. What does it mean? It means that he pays, he paid the game. The first game he may got 5 or minus 3. Second game he may got 5 or minus 3. But then if we look at a bunch of games that he pays, then we look at all this and sort of take an average, then you will find that he will lose $1 per game. So it's not good for him. It's not a fair game. All right? So he'll lose $1 in the long run. This is a term that we use in probability. That means if you just toss, but just play the game once, so the gentleman can get 5 or lose 3. Okay? Only this. But then if he keeps playing, then sometimes he got 5, sometimes he lose 3, but then on the average, all right, he lose 1 per game. All right? Okay. Example 2. We roll a balanced die, and C is the amount that you pay for the game. And you will get $I if the number I show up. So how much he has to pay? That means how much is the C? So that his expectation of gain is equal to 0. That means it's fair to the player as well as his opponent or the house. So gain is the random variable. So here, okay, we start with doing something simple before we talk about gain. X is not the gainer. X is the amount that he gets. All right? So what are the possible values? He will get 1, 2, 3, 4, 5, 6. One of these values. Depends on the outcome of the die. All right? So X takes 6 values. And what is the probability of 1, probability of 2, and so on. So because there's a balanced die, so it's 1, 6. 1, 6. So the expectation of X is equal to 3.5. So in other words, on average, we expect he get 3.5. 3.5. All right? But we have not considered or take into consideration the money that he pays. So now I define, okay. So now he has to pay if he paid $3.5 to play the game, so every time he play, he have to pay $3.5. All right? He may get $6, he may get $1. All right? But then in the long run, he will not gain anything and he will not lose anything. All right? So we just take C to be the expectation. Of course, alternatively, you can create a new random variable. Let me call it Y, which is the amount that he gains. It's not the amount that he gains. So gains is the amount that he get minus the amount that he pay out. So the amount that he get is X. The amount that he gain out is C. All right, so you have to understand why I define it like that. Remember, X is the amount that he get. All right, C is the amount that he had to pay out to pay the game. So the difference is the money that he gained. All right, so Y is equal to X minus C. Is X a random variable? The amount that he get is a random variable. Depends on the outcome of the die. Is C a random variable? Is C a random variable? If it's a random variable, what are the values? No, C has only one value. Each time you pay, you have to pay this amount, C dollars. So C is a constant. How about Y? Is Y a random variable? Is Y a random variable? Why I have to ask this question? Because if it's constant, you don't have to do so much work. A constant will always the same. All right? Same value, Y means. So is Y a random variable? Of course, it is a random variable. Why? Because it consists of two components. One is X, the other is C. X is a random variable, although C is not. But then the difference will be a random variable. So if a random variable, we have to ask what are the values. So these are the values. And what's the probability? The probability of Y equal to 1 minus C is 1/6. Y equal to 6 minus C is also 1/6. All right? Because probability of Y equal to I minus C is the same as probability of X equal to I. All right? So this is important. All right? The calculation is very simple, but I want you to understand. I approach this problem, the expected gain, all right? I make it to 0. So what should the C is? This is the original question. So one way to do it is I got the expectation of X, how much he will gain, and then put the C equal to that value. That will make the game fair. Alternatively, I look at it from a more structured way. So I define a random variable Y, which is the amount that he gains, which is the difference between what he gets and what he pays out, the difference between these two. So what he gets is X. What he pays out is C, so it's X minus C. So it's a random variable. This Y is a random variable. So the next question is, what are the values of this Y and what are the values of so what is the probability of this random variable for given values? So probability of x equal to I minus c, I is the outcome, I equal 1, 2, 3, 4, 5, 6, is the same as probability of x equal to I. Because y equal to I minus c is exactly the same event, equivalent event as x equal to I. All right, so it's 1, 6. So we work out the expectation of y, which is 3.5 minus c. All right? It's just a mathematics, right? 1 times 1, 6 plus 2 times 1, 6, and so on. So it gives you 3.5. And then minus c times 1, 6, minus c times 1, 6, and altogether there are 6 of them. So it becomes minus c. So in order the expectation of y equals 0, the c must be 3.5. All right? So you arrive at the same answer. Yeah. Okay. So here's another example. I think, I leave this example for you to read it. But basically, it is you pay out this amount, all right? 50% loss, 25% loss. So this is the amount. 100%, this is 100% is the amount. So 50% is half of it, 25% is 1/4 of it. And these are the corresponding probabilities and so on. All right? Then what you have to do is to calculate your expected payout. Okay, there's a very small chance that you may pay $1 million, but there's about 1% chance that you will pay 10%. That means 100,000 and so on. But you want to make a profit, so you have to charge the other guy what you expect, the loss that you expect. That means expect payout to the clients. On top, you also want to make profit, so you have to add this amount. All right? So this is the expected loss. The chance of loss 1 million, the chance of loss half of it, and so on. So at the end, we work out that you expect to loss for this particular policy is 4,200. All right? It's important to make it complete. You won't lose anything. If nothing happens, you don't have to pay out, and the chance is 1 minus all this. All right, so altogether, you only expect to pay 4,200. This is the expected loss. If it's so bad, it just happened, some accident, and you have to pay out 1 million. So that's the amount that you pay out. But you have to average out, sort of. So this policy have a very slim chance. I mean, there's a slim chance that you pay 1 million out, but as an average, you only pay 4,200. Presume that you have many, many policies. All right? But, so if I charge the clients 4,200, I break even. I won't gain anything. All right? On average, I don't gain anything. So I have to add 5,000 to this amount so that I can make a profit of $5,000. All right? So I charge 9,200. Okay, so now we have this sales x, okay, between 0 and 1. The density is given by this one. So what is expectation of x? So this one is just do the integration and 3x. So you expect the sales is 3x, all right? Okay, now this is slightly different from the previous one. So we are still given a PDF, a distributed with PDF, and try to work out what's the expectation. But as before, the f of x with different form, 3 forms, over 3 different regions. The first one is x between 0 and 1. It takes x. The second one is x between 1 and 2. It takes the form 2 minus x. The third one is otherwise. That means outside 0 and 2, it will be 0. All right, so we find the average number of hours. And remember, here, all these are 1, 2, it means in a unit of 100 hours. So this may not be important, all right? But you have to understand all these are x, the little x here is range from 0 to 2. But in fact, 1 unit means 100 hours, all right? So in fact, this is how the PDF look like. X, 0, 1, 2, 0 here, and then x. All right? And then between 1 and 2, then it comes down and flat. I guess it's like that. All right? So this is the PDF. It looks like a triangle. So find the expectation of x. So we do the integration from minus infinity to infinity, x times f of x. All right? As I said, you have to divide into 3 regions, in fact 4 regions. From minus infinity to 0, which is 0, and also from 2 to infinity, which is also 0. So these 2 are gone. So you're left with this one, complete the integration, and you get the answer, which is 1. So you expect the number of hours used is 100 hours. So some use less, some use more, but it seems that based on this PDF, the maximum is 200. No one go beyond 200 hours. 2 units, 200 hours. So we expect it's 100 hours. All right? So the vacuum cleaner, the number of hours used is 100 hours per year. Okay. So expectation of function of a random variable. So it's nothing new, except that we are looking at x is a random variable. So g of x is also a random variable. G of x is just a function of x. So an example is like x squared or x minus mu squared. All right? Or e to power x. These are some examples of function of x. Because x is a random variable, a function of the random variable is again a random variable. Function of a random variable again is a random variable. All right? So if x with a probability function or probability density function as f of x, then the expectation of the function of x, you just, this one, you replace it by gx. So expectation of x for discrete case is sum of x times f of x. So if you replace this by g of x, then you replace this by g of x. All right? So that is how you obtain the expectation of function of x. For discrete case, for continuous case, you just do the integration. So again, for continuous case, it's supposed to be integrate x f of x dx. All right? And you replace this by g of x, so you replace this by g of x. By the way, just a word of caution that I saw sometimes you make some of the students make a careless mistake. When they find expectation of x, expectation of x, or for continuous random variable, then they just do it like this. All right? They forgot about the definition. There should be an x here. Without the x, wow, you get the 1. Because without doing, I know that it must be 1. You integrate it, it has to be 1. All right? So you pay attention. Expectation of x, you have to x times f of x. Do the sum or do the integration. Expectation of g of x, a function of x, then you just the g of x times the f of x, do the summation or do the integration. So remember, you have to multiply the g of x by the corresponding f of x. All right? Okay, special case. So if g of x is defined as x minus mu x squared, this is a function of x. How about mu x? Mu x is just a constant. What's mu x? If you remember, we defined it as the expectation of x. This is a constant. So this basically is a function of x, or you can write it as x squared minus 2 mu x or mu times x, and then plus mu x squared. Okay, if you find it confusing, I just drop the x. All right? Drop this mu x, the x subscript in the mu x. I want to put an x there because I want to tell you that, okay, this is the mu, which is the expectation. Expectation of what random variable? The random variable x. All right, so that's why I put a subscript x there. All right, so if I write mu of w, then this means expectation of w. Of course, I need to tell you what w means. All right, so in for special case x minus mu squared, then this leads to something called the variance. All right, this is the variance. Variance, defined as the expectation of the square of the difference between x minus mu x. Sometimes we denote it by sigma square. All right. So, okay, there are a few things here. First of all, what does that mean? It basically means that, okay, I look at the difference between the particular x value and how far it is away from the center, which is denoted by mu x. By mu x. Look at the difference x minus mu x. And in fact, I not just look at the difference, I square the difference. So to make it bigger if the difference is big. Okay, if the difference is small, you square it, it's still very small. But if it's big, think of it, if the difference is 2, you square it, becomes 4. But if the difference is 10, 5 times only, then when you square it, it becomes 100. It becomes 25 times. So I expand or try to make it bigger, so I square it. So we basically measure the square of the difference of x from the center. And then I add up all this difference or integrate it. So that it tells us how the x are away from the center. If this quantity, this expectation of x minus mu squared is small, what does it mean? It means that x minus mu, the x are very close to mu. So that's why you get expectation of x minus mu squared is small. Now if this quantity is big, what does it mean? It means that these values are big. Not only that, the chance or the weight for this big x minus mu squared also very big. All right. So maybe give you a picture. This one and this one. So this is the center. This is the center. So for this case, this represents a PDF. So for this case, the x are more concentrated around the center. For this one, it's more spread out. This will give you big sigma square. This one will be a relatively smaller sigma square. All right? So this quantity is variance, defined as the square, expectation of the square of the difference between x minus mu. Then, if you remember, you have this formula called sample variance. All right? This is for sample. It's not for the population. Here we're talking about the population, which represent by the random variable x. All right? This population, the values are represent the behavior of this population represented by the distribution of the random variable x. All right? So then this expectation of x tells you the center of this population values, and the variance tells you how spread out the data. And this one is only for a sample, not for the population. All right, you take a sample and you calculate it. It basically it's the same idea. Calculate each individual, measure how far they are from the x bar. X bar is the average of all. Then you square it and then take the average. So if you divide by n, then it's exactly the average. But because of some mathematical reasons, we divide by n minus 1. So to make it unbiased estimator. All right. So we'll come back to this. But anyway, you have to distinguish between your sample variance formula and the population variance. This formula that I show you, expectation of x minus mu square, that is for the population variance. Tells you how the whole population behaves, how they vary, where the variation is big or small. This formula is for sample variance. This only tells you something about your sample, how the variation in your sample. All right. So, so you have to be aware of that. So these are the formula. And the variance of x is always bigger than 0. And the variance of x can be shown equal to the equal to a difference of two quantities. One is the expectation of x squared. The other one is the square of the expectation. Hey, it looks similar. Are they the same? Obviously, they are not the same. Okay. Now, it's very important now. This one is to square the random variable first. You create a new variable, is the square of the random variable x. Then you take the expectation. While this one, you take the expectation first. After you take the expectation, it becomes a constant. You square this constant. These two are not, these two are not the same. So in other words, whether you take the square of the random variable first and then take the expectation afterwards, or take the expectation first and then square it, the answers in general, they are different. In fact, almost always are different. All right? So it's a make sure that these are different things. And the square root of this variance is called standard deviation. Standard deviation. Let me just repeat it. It's the standard deviation of the population, which represented by the distribution of the random variable x. All right. Okay, so another special case is gx equal to x to the power k. It's called case moment. Can we have this? Right? We can have this. And we also have a name for it. This is called case moment. So what do we call this? It's also to do with case moment, but it's called case central moment. Central, because its expectation of xk is relative to 0. It's x minus 0 to power k. So the second one that I wrote down here, okay, this one is x minus 0 to power k. So it is just the case moment. This one is relative compared with mu, which is the center. So this one is called case central moment. Central moment of x, of the random variable x, of the distribution of x. All right? Okay, I think I have to stop here. And we'll talk about the examples and try to finish this chapter next time. Okay?